time that I like is the proof of Schrodinger hypothesis for physical assumptions based on quantum theory. And more recently about using, well, the application of quantum, if I may say, some differomorphisms in the quantum cellular domain. And the work that also is interesting for this community. So, thanks again for coming, and we're looking forward to your talk.
Okay, thanks a lot, Czeslaw, for the introduction. Thanks a lot for the invitation. So, just to say that at University Paris-Saclay, we are starting a QUACS, Quantum Computation Structures group. We are 5 permanents now, and we are actually hiring a 6th person. This is a group that belongs to a computer science laboratory, the Laboratoire de Méthode Formelle. What I will be talking about is joint work with Amelia Durbeck, who was a PhD student with me, and Matt Wilson, who is currently a PhD student at the University of Oxford. So, to introduce the topic, I want to make a few considerations about your good old pedestrian tensor product. So suppose you have 3 systems. Those are 3 systems. They are named U, V, W. You could name them Alice, Bob, Charlie. They carry some internal state, like white, black, white. Well, you could decide to re-express this, splitting this with a tensor. So for instance, you could view this as a tensor product between system U with, on the right-hand side, systems V and W. But you could also decide to express this according to that tensor product. So you have UV on the left and W on the right. And these 2 things are equal, but in a sense, well, you see that this symbol here isn't quite playing the same role as this one. This is not the same tensor. It's not doing the same split. And so if I wanted to be a bit pedantic, if I wanted to be more precise in my notations, I should really be saying that here I have a symbol that's doing a split by keeping the U, whereas here I have a symbol that's doing a split by keeping U and V on the left-hand side. Okay.
But is it implicit that there is a tensor product between V and W, like in the very first? How do you group V and W? Is there?
How do you group V and W? You could.
But
you could.
Is there an implicit tensor product between V and W as well, or not?
So I'll come back to the formal definition of the whole Hilbert space, but you could just consider this as a large Hilbert space of graphs, if you like, of sets of nodes. Okay. So the point I want to raise here is that there are different kinds of tensor products, and in general they are parameterized by some discriminating function. And so we may start to wonder, okay, discriminating functions, what kinds of discriminating functions work and serve the purpose of parameterizing these kinds of tensor products? So for instance, we could consider splitting this state not according to the names, but rather according to the state, to the colors of the nodes. So here is another tensor product, if you like, parameterized by mu, and that mu stands for marked, and it keeps on the left-hand side the unmarked nodes and pushes away on the right-hand side the marked nodes. Okay? And so I could start writing things like that, it's something that, you know, it's a bit like a tensor product, but it's also a bit like a direct sum. It's something a bit in between. Anyway, so the fact is that if I consider this superposition here, I will have to split it according to mu as this sum here. And you see that something interesting is happening already, because the way I'm placing my systems left and right of the symbol is already quantum. Because the discriminating criterion is quantized, the split is also quantized in some sense. Okay.
So I have a quick question.
Yes?
Where do these objects live? Are they in a vector space? And is that quality strict quality, or is it like a...
Yeah. I'm in the sort of motivation phase here. And then I go into the formal stuff. And so I answer these two questions, I think, are of the same nature. Right. Just another remark I want to make before I define the Hilbert space is that, so now you have these mu's, these chi's, etc., and you start being able to write the same state, but split according to different kinds of tensors. So this is the chi uv tensor that keeps u and v on the left, and w may be in a superposition of being white and black. And this is equal to, well, I'm going to take this and split it according to the mu tensor. And the thing I notice is that this was product state, but this is an entangled state. Okay, it's not completely surprising. I mean, we already know that some states feature entanglement depending upon the way you would split your Hilbert space, but that's another way of stating it.
So I guess you will go to this, but already here you mentioned there is distinguishable property. This is white or black.
Yes.
And there is just name, which is not a distinguishable property.
It is a distinguishable property as well.
It is a distinguishable
Yes.
property.
Yes.
So there is some property that associate U, like property U.
It is, okay. So my plan of the talk is to define properly these generalized tensors and traces, to then explain why they are not just crazy symbols that one may, a mathematical delirium, why they actually work, and then go into applications. I want just to mention at this stage that my motivation, I never wanted to define these generalized guys to begin with. My aim was to consider quantum evolutions over networks, superpositions of networks, and that's how I ran into these things. So those will be part of my applications. Now, I'm going to spend some time on this slide because I think I've got 3 questions that are on this slide. Okay. So let me define a purely classical object, which is what I call a system. A system is just a node that carries a unique name. So if you want to have a unique name, you'd rather have a lot of names. So V is the set of possible names, and it needs to be an infinite set, a countably infinite set. And it has an internal state. And this internal state is in some set sigma, which is usually taken finite. For instance, it could be black and white. Okay. Now, what I call a graph is just a set of these things where each name is different here. And I can only consider finite sets of these things just to make sure that there is a countable number of such graphs that will help me build the Hilbert space later. What can I say? I call this a graph, even though there are no edges at this stage, but I will introduce edges later in the talk. At the moment, it's not important. Now, if I change a color, it's a different graph. If I change a name, it's a different graph. There's plenty of graphs here. There's a set of them. It's called curly G. And here is how I build the Hilbert space. The Hilbert space is just that Hilbert space whose canonical orthonormal basis is exactly identified with the elements of curly G. Therefore, a valid state, a psi, is just any superposition with whatever amplitudes of whatever graphs. I hope that answers the questions.
It's like one small question is that
okay.
How do I know that when I give the name W, it's not actually the same thing, like not a different object? Do I know that there are three objects? Do I know that the black is in between such that the right from the black I can call W and the left from the black I call U? Like so how do I know that there are enough objects that are distinguishable by something, that there is no maybe one white object? And now you call there is U and V. And so how do you know that there are two objects? Is this assumed that there are two objects?
It's assumed. So my graphs, a graph is valid if all of its nodes are named in a unique way. There shouldn't be two nodes with the same name.
So two graphs that look the same but are differently named with respect to the inner product of the Hilbert space are orthogonal.
Yes.
Are you making a difference between the graph and the graph in bracket?
Yes, I should be. I mean, maybe I forgot sometimes to do it, but yeah, I ought to be. I mean, it's the same difference that there is between the number 1 and the state ket1 in some Hilbert space. Yeah. Okay. So now I'm talking about tensors that are going to be parametrized by some kind of a discriminating function. But not all kinds of discriminating functions work. Actually, when you do the math, you find out that you cannot just take anything. You have to take functions that we call restrictions. And here is the condition that they must meet. So let me explain what I've got on the board. So chi is the thing that takes a graph, just a basis state, a classical thing, a graph, and it tells you which part we should keep to go on the left on the tensor. So it maps G to G of chi. G of chi is the smaller part. It needs to be a subset of the whole, in the sense that, for instance, this node U is a subset of this graph here, where there is both the node U and the node V. Okay. And the property that we need to have a restriction is the property that we arrived by the need of the mathematics, is that if some graph, so for any G and H, so if this H is included between G and the restriction of G, then the restriction of H coincides with the restriction of G. So it's kind of a relatively intuitive condition. For instance, the examples that we had before, they do obey this condition. So in the examples we had before, chi of U is the restriction that keeps the system U. Mu is the restriction that keeps all the white nodes. Okay, those are examples. So just to understand a bit more this condition, you will find that it entails idempotency. If I restrict according to chi, and then I restrict again, it doesn't help. I mean, just it's a projection in that sense. It's also, if I restrict under chi and then I look at the complement of chi, then this is the empty graph. So this chi bar is, what it does is that G of chi bar is the rest, right? It's G where I took out G of chi. For instance, it's the black nodes, the leftover, the thing that goes to the right. So, okay, so it's kind of, it's very close to idempotency, this condition. And it has some nice properties. For instance, if chi and zeta are restrictions, I can build up chi union zeta, and that's going to be a restriction. And later, when I go to graphs, I will find that if chi is a restriction, then chi R, that is the restriction that restricts not just to chi, but also to the R neighbors of chi in the graph, is also a restriction. So basically, I'm saying that this thing here, these restrictions, you cannot do anything. You cannot do two crazy things, but you can do a lot of things. Okay. So now that I've defined the set of restrictions, the set of discriminating functions that I can put there to parameterize my tensor, let me define this tensor product. So first of all, notice that now I'm viewing the tensor product not as a constructive thing that takes Hilbert space A, Hilbert space B, and builds up Hilbert space AB, but rather I am viewing it as a analytic thing that is going to split a very large Hilbert space of graphs into two graphs. Okay, so it's from a superposition of graph on the left-hand side, a superposition of graph on the right-hand side, to a superposition of graphs. It's internalized now. It's a binary operator on a single Hilbert space. That's what I mean. Okay, so how do I define it? Well, first of all, I just demand that it be bilinear. Any tensor product should be bilinear. And then it suffices to define it on basis states. And the basis states, they are graphs. So let's say that I have a graph on the left-hand side and a graph on the right-hand side. Well, if it so happens that there exists some G which is such that the left-hand side is G of chi and the right-hand side is G of chi bar, then the result is G. Otherwise, I just yield the null vector. So it's a tensor product that sometimes yields the null vector. Okay, that's a bit of a leap to take, but it turns out that it works very well in the mathematics afterwards. Okay, so let me give you some concrete examples of this tensor product. So we had chi u. So we already wrote this equality earlier on, so that still stands. I mean, when I look at this node u and this node v, well, they can very well be part of a larger graph G, such that this is the chi u, and this is the bar of the chi u. So fine. So then this binary operator yields back this state. Okay. But if I look at this graph, well, there is a problem here because chi u would never have given you back v. Okay, so that goes to 0. And if I look at this operation, there is a problem because chi u would never have left behind u on the right-hand side. So there is a problem, so it yields the null vector. Yes?
Just to double check, the linear space H is the same. All the free H are really the same.
Yes. Okay, so it's basically taking any graph, seeing whether they are compatible according to this criterion, and gluing them back. And if they are not, you yield the null vector. Okay. Right. So you can define the tensor product over operators just in the natural way you would do it, right? You just do the tensor of this guy and this guy and this guy and this guy, and here is the tensor of operators. Okay. There can be some subtleties, and I've kind of graded some subtleties and the fixes to these subtleties, and so perhaps if some question orient me towards that, I will go back to it. But okay, that's what I want to say for now. Okay. So the cool thing is you have a tensor product, but you also have a partial trace associated to this chi. So the partial trace, okay, I wrote it like that, like a restriction to chi. It's tracing out the complement of chi. And so it's something that takes operators over the Hilbert space, but not all, right? I mean, traces, they can only eat trace class operators. For instance, if you take the trace of the identity in a huge Hilbert space, then you get an infinity. So, okay, so you take trace class operators to trace class operators. Again, notice it's the same Hilbert space here and there. It's not from AB to A, right? Okay, and how is it defined? Well, because I just say it's linear, I have to define it just on basis states, and the basis states, they are those Kg bra H, right? So how would I want to trace this out? Well, I really want to keep the restriction of G on chi and the restriction of H on chi. But the partial trace, that's not the only thing it does. It also compares the rest, right? It does a trace on the rest. And the trace on the rest is checking that these two are equal on the rest. Okay. And so let me give you some concrete examples of that. If I have this ket bra here, well, you see that the rest, whatever isn't u, is equal. And so this is going to be a 1. And so what survives is this part. There is a mistake. It should be a u here. Here, the rest is different by the color. So this gives you the null vector. Here, the rest is different because it's just not there. And here it's there. I mean, it's different by the geometry, if you like. And so it gives you the null vector. Okay. So just to reassure you a bit, this map here, this thing that maps density matrices to density matrices, is indeed a quantum operation. It's a trace-preserving, completely positive map. So in that sense, it's a very sound operation to do on this Hilbert space, on this density matrices over this Hilbert space. Okay. It's also got some.
How can it be trace preserving if you can get 0 on the other side?
Yeah, but you get for the trace as well. You can get 0 if you trace ket G and ket H, and if they are different, then the trace is just going to yield you 0, right? The trace is only keeping the diagonal terms.
So if you have something like GG, you will always get.
You will always get 1, yeah.
Okay.
Yeah. Okay, so it's got some good properties. For instance, if some restriction is included into another, then you would expect that, if you take rho and you trace out just to keep chi, and then you trace out to keep zeta, because zeta is included to chi, then it should be equal to the same, it should be the same as rho, as the reduced density matrix over zeta, right? So you get this. However, you have to be a bit careful with the notion of inclusion of a restriction, and there is some condition here that is not so easy. So this is why we call it comprehension. And again, it turns out that when you actually place yourself in the world of graphs, you look at radiuses and so on, if your superpositions they have the same names appearing, then this whole condition vanishes. So, I mean, I'm just saying that there may be some subtleties here, and I'm willing to go into this. But, okay, right now let's keep to this picture. Okay. So, here we are. We introduced a symbol for a generalized tensor, some generalized trace. Okay, why not? But why? I mean, and after all, what is the criterion for success here? I mean, why do we use tensors and traces to begin with in quantum mechanics? What's the point? I mean, why do we use it? So, I mean, my answer, but I don't think there are many answers to this question, is because we need to have a notion of places of different systems. We need basically to have a notion of locality and be able to say what is local to some place. We need to have notions of causality, when it is that a place can signal to another place. And that's basically why we use tensors and traces, I would say. Okay. So the point is that there are plenty of facts about locality that survive, that just carry through to these definitions of the tensors and the traces. So what do I know? I mean, if I open some standard quantum mechanics book and I try to look at notions of causality, what are the main lemmas, the main properties that I may have? Well, here is one, for instance. If A is a local operator, so first of all, what do I mean by a local operator? Intuitively. Intuitively, I mean that, I had plenty of systems, but I act upon them with some operator A, and if this operator is chi local, what I really mean is that it's only looking at the chi part of my systems, and that's the only thing it's changing, and the rest is unchanged, intuitively, right? That's what I mean by locality. Okay, so now, if I want to be more precise, if I want to phrase that perhaps in the Schrodinger picture, where I've got G that evolves into H, and I'm wondering about the transition amplitude between G and H, what does locality mean? Well, locality means that first of all, this is going to be 0 if G and H do not coincide outside of chi. And this is what this bracket is saying here. And second of all, this amplitude should only depend on what happened here and there. Okay, so it should be some sandwich here where this is the only place where A is appearing. So that's a Schrodinger-like, a transition amplitude-like way of stating the locality of some operator A. I've got some other operational way of thinking about locality, which is just to say, well, something is local if really I'm applying something here and nothing there, right? So something is local if I can express it as something at k, and nothing, I mean the identity, on the rest. Okay? So that's the sort of operational notion of locality. And here is a more Heisenberg-like way of thinking about locality, where I think of A not as an evolution, but rather as an observable. And if A is a local observable, then surely it should only depend, the result of the observable should only depend on my reduced density matrix at that place. Okay, so if I'm looking at this table, then the result of my observation should only depend on what's on this table. Okay, and so that's this equality here. The probability of the outcome that corresponds to this element of some P of M, for instance, should be equal to that in which I replace rho, which was the entire graph, with the reduced density matrix of rho at chi. Okay. Well, it turns out that all of these things are completely equivalent for the notions of tensor product, of reduced density matrix that I gave you earlier on. Okay. Okay. It's not. You need to check a lot of things. It's several pages. This is why the paper is 30 pages long, but it just works. So, okay, just to give an example, maybe I should have started by that. What do I mean by local? But for instance, I could mean that there was a spin at system V, and I'm applying a certain coin to that spin. In the language of quantum walks, for instance, I'm applying a coin to the coin degree of freedom of the walker. This would be the unitary C. Okay, just to give an example. Okay. Right. Let me just skip over that for now. Okay. So that's good. What about causality? So first of all, what is causality? I mean, what is the difference between locality and causality? Sometimes we get a bit mixed up. So what I mean here by causality, I have it here in that picture, intuitively. What I mean is that, okay, there's a bunch of systems here. There is a big graph or a superposition of graph or whatever. This is going to evolve according to some big unitary operator. So now everybody is evolving. However, I want this U to be chi zeta causal. What do I mean by that? I mean that whatever lies at zeta at t plus 1 should only depend on what lied at chi at time t. That's what I mean by causality. So, okay. So let's be a bit more concrete about that and provide mathematical definitions for this. Okay. So here is the Schrodinger way of defining causality. Yes. Well, it could depend on, I mean, an operator could not be causal. It could be causal with respect to a certain zeta and chi, or to a family of zetas and chis.
What I mean is you don't have a speed of light here, right? So it could be bigger or smaller. What determines?
So right now, I'm in full generality. I haven't told you what zeta and chi are, and these theorems, they are true for any zeta chi causal unitary operator. Yeah, whatever the restrictions zeta and chi, etc. So, but if I take this example here, then this is a typical example of a causal operator. It's something that moves particle, right? So, for instance, this is a particle that's about to go to the left. This is a particle that wanted to go to the left, but it's going to have to bounce because the line is just finished here. So after one time step, this guy has bounced and this guy has moved to the left. So if I want to determine this state from that state, there is a zeta v r, where r is radius 1, causality. So what I mean is, so if zeta v is the restriction that focuses on v, and zeta v1 is the restriction that focuses on v and its first neighbors, then M is zeta v1, zeta v causal.
In general, for some local interaction, we have limp Robinson bound, which gives you, I guess there are some.
Yeah, so
They're not very strict. Sometimes they go outside a little bit, but.
Yeah, okay, so but I'm a very, perhaps in that sense, very Chomsky person, and I'm really looking at discrete time evolutions here, and I'm looking at strict radiuses of locality in discrete time. So Lieb-Robinson bounds could be some approximation of that if you integrate for a certain time, etc. Yeah, but okay. Yes? Yeah, zeta is some restriction, chi is some restriction, and I'm saying, and here I'm saying.
Then you can draw that picture, but I don't understand where this is causality.
Okay, I'm saying that in the evolution U, whatever feature zeta is fully determined by whatever feature chi previously. That's a bit abstract. Okay, if you want to just instantiate this as an example, you should just think of zeta as focusing on one node and chi as the node and its neighbors.
Okay, so zeta chooses a part of the graph, and if the property tells you that this part of the graph, the properties here are determined by the subset of the graph of the t-1 chosen by x, by I.
Yes. Yeah. So this is determined by this. Yeah.
But this can be, in the big graph, you can choose different nodes and subsets here and there. Also.
Yes, I mean, yes. Okay, let me just. Yeah, I'm not sure I understand the question.
No, just trying to understand.
Okay.
Yeah.
It's really. I mean, it's really there to speak in a mathematical manner about the finite speed of propagation of information. Okay, in your structure.
Yeah, my issue is that you haven't said yet. You said what is time, but you haven't said what is space. So how do you get the speed?
Yes, that's right. But so when I will speak about graph, I will say what is space for me. But in a sense, I'm leaving this free for the user of this theory. You could choose your own chi, choose your own zeta, decide whatever is space for you in whatever formalism. Okay. Okay. So this is causality in the Schrodinger picture. Why? Because I'm saying, let me take some rho and evolve it into a rho prime, and let me focus on the reduced density matrix at zeta. So let me look at rho prime of zeta. Well, to compute this guy, I really didn't need the whole of rho. actually, I could replace rho by rho of chi and evolve that instead and take the reduced density matrix, and I would get exactly the same result. This is causality, the Schrodinger picture. Causality in the operational picture will be that this big U is actually a circuit of little local things that of little interactions that kind of compose to and compose and conspire to compute U. Okay, and the Heisenberg picture of causality is this idea that, let's say that I measure something so let's say that I have some observable A that sits here at zeta at t plus 1. Well, whatever I could measure at t plus 1 according to this local A should be something that was measurable at time t in a slightly enlarged radius, but still something local. So it should be something, it should be actually this observable, and this observable should be chi local. That's the Heisenberg way of phrasing causality. It's the one that is used, for instance, in algebraic quantum field theory and stuff like that. Okay. Yeah?
Showing you the slide before locality, I'm not sure to get through the difference between locality and causality.
Yeah, so
The picture is very similar.
a local guy, locality is not changing anything but a part. So it's like I'm freezing the room, you guys, the time doesn't evolve for you, and now something is happening here at the desk. Okay? I'm just changing a little part of my subsystem, and the rest is totally unchanged. I changed the chi part, and I apply the identity on the rest. Whereas causality is more like physics as we know it. Everybody is evolving, but everybody is evolving only according to local
It's defining a sort of ordering relation, containing relation of self graphs.
Yes, it's yeah. You could say that. It's saying that chi stuff can cause zeta stuff. So it's introducing. You could say that there is some underlying poset structure there. Yeah. Okay.
Is there an implication on if you use causal then it's local?
If there is, it would be in the other direction. I think if I think that any local A, any chi local A is chi causal. But yeah, usually causal guys are not local.
We just it's a slightly different notion of causality than what people use in GPTs with unique effect and all these things, because you embed somehow really time directionality in a sense. And so the choice of row in a down, you can choose maybe some different initial conditions, and then you have later on different state. But the other way around will not work. If you choose different something like that, will not have any influence down. So it's somehow it's a very strong notion of causality, because you embedded that there is a flow evolutions in one direction. Which is the normal. I mean, this is the one we I'm just trying to connect.
Yeah, but you can prove that if U is causal, U dagger is also causal. It's a property. And yeah.
No, I'm just wanting to in the GPTs you have a notion of free choice, signaling, all these things, which can be represented here, I think. Like the free choice will be the free choice of row reduction of chi in the lower slice. And then you see there is some different different effects later on. And in the GPTs also, people say, oh, what? I do though different things. I choose different measurements later on later slides. And what is the condition that I actually don't have any differences on the previous slides? Then they formalize this. I think this is somehow embedded in your causality and it's very natural.
Okay.
Can I just ask for
Yes?
clarification? Because this is where I was confused. So, okay, again, it's different, I think, than saying what's a light code structure. Because somehow, let's assume that you had a speed of light, and that code was actually bigger, but there is nothing outside that circle. This would not be captured here. This is about what a specific evolution, it's what depends on what in the previous slides, but it's not on what space-time region could have depended on. So if these nodes are empty and there is nothing, is it still going to be included there? This depends on the evolution you have, that's what I'm trying to say. It doesn't depend on the properties of the graph only.
Yeah, causality is a property of U, not of the graph. Yeah. Okay. Right. So we introduced generalized tensors and traces. We showed that they are very strong in terms of all the mathematical artillery that we are used to in order to talk about locality and causality. I mean, everything carries through. So, okay, fine, but why? I mean, what for? Why should we bother with these things? So, since I'm in the mecca of quantum reference frames, I thought a bit about that, in particular with Anne-Catherine the other day. So, here is perhaps a certain connection that we could make. So here are two graphs. Again, I haven't introduced my edges yet, but anyway, I could just say that this is not 0, not 1, not 2, not 3, etc., and that they have neighborhood relations that way. For now, it's good enough. Okay. So, and I could superpose these two situations here. So there is maybe Alice that is represented by a white node. There is Bob represented by a black node. And I could decide to just take the viewpoint of Alice. What I mean by that here is just that I introduce a tensor product which singles out Alice on the left-hand side. Okay. And so what happens then is that whatever the superposition, Alice is on the left-hand side, and she's white, and on the right-hand side, you have this superposition of graphs. It's taking the view of an observer, Alice, which is a superimposed observer. In that sense, it is a bit, it is giving some steps towards quantum reference frames, but it's not quite the same spirit as quantum reference frames. For instance, here, we keep the fact that Alice's name of node may be 0 or 1 in a superposition, and that this is entangled with everybody else's position here. I mean, this is so this is entangled in particular with Bob's position in the rest of the graph. Okay, so it's just taking a half. It's doing half the job as what quantum reference frames would do. Okay. Some other motivations to look at this. Well, we're in the mecca of several topics. Another one is indefinite causal orders. So let's look at here a superposition of causal orders where I can do U and then V, or V and then U. Okay. Where is my control bit here? Well, it's the geometry is the control bit, if you like. Never mind. The point is that this first wire in this circuit, it can signal to the last wire. And in this circuit, it can't. But the last wire can signal to the first wire. So this is a kind of space-time thing. But if I want to flatten this into space and draw the interaction graph that is at time t, who do I know is capable in one time step of sending a message to some other guy? Well, that's the interaction graph. Right? The interaction graph in this picture is that the first guy can signal to the third, and in this picture, the third can signal to the first. So what I'm saying is that behind this idea of indefinite causal order, there is, in fact, an idea of superposing posets, causal relations, and in fact, superposing geometries. Okay, so here you have these superpositions of graphs appearing. Another place where they appear and where they appeared quite a long time ago is in quantum gravity, and in particular loop quantum gravity, but also causal dynamical triangulations and several other families of theories. And in those theories, space-like cuts of space-time, then they tend to be discretized, for instance, as simplicial complexes, but sometimes you actually take the dual of the simplicial complex and you just get graphs. And then these things evolve in time. Usually they don't evolve in time according to a unitary. Usually the formalism that is chosen is that of some kind of a Feynman path integral, and you actually look at little regions of space-time where you would do this. But anyway, the point is that in quantum gravity as well, you have quantum superpositions of graphs. And I would say that both in indefinite causal order and in quantum gravity, there are these quantum superpositions of graphs, but actually little has been done to formalize, to give proper mathematical definitions of what they are. What are quantum superpositions of graphs? So this is one thing that needs to be done. And another thing is that, okay, if you have indefinite causal orders, how do you get there in the beginning? How do these indefinite causal orders evolve? What are we allowed to do in quantum gravity? Can we just signal from here to there? Should we respect some kind of a unitary constraint? I mean, evolutions in quantum gravity, they shouldn't be just, they shouldn't ignore quantum mechanics altogether. You would think that they should be unitary, they should be causal, but unitarity and causality of the evolutions of quantum gravity, they are very poorly understood properties. Okay. So here are basically two motivations to consider what I call fully quantum networks. That is, things where you can superimpose entire graphs, define them properly, look at evolutions upon them. Okay. Right. So if you want to start doing this, you will very soon hit some rather difficult questions, like very basic questions. You stumble upon them. I mean, so let me tell you two difficulties that have got me crazy for a number of years. So now my Hilbert space is meant to have graphs, right? So not just sets of systems, but sets of systems that are possibly connected by edges. Okay. So let's say that I want to import my earlier machinery. I want to be able to do these tensor products. So let me do the tensor product of this node here with the node V. What should I get? Should I get UV disconnected or connected? That is, when you have a graph of systems, you also have connectivity between those systems. If you want to put a tensor product in between, where does the connectivity across the tensor product go? Okay? How do you split stuff into subparts when there are edges between the parts? Okay? That's something that's kind of annoying when you start thinking about this subject. Another thing that's rather annoying as well is, okay, forget about edges. Just let me imagine that I want to evolve my graph in a way that is capable of creating new nodes. Okay, I want to alter the geometry. Maybe I want to inflate the universe or whatever. I mean, I just want to be able to spawn a new node. Okay, be it connected or not. I mean, the fact that it's connected or not, it's not important here. Now, the thing is, if I'm going to create a new node, how am I going to call it? Could call it V, could call it W. Okay, but the thing, this U here, it needs to be a reversible process. If I call it U or if I call it W, it's not the same thing. And in particular, for instance, if I apply U dagger to this, it should give me U. And if I apply U dagger to this, if this is unitary, it shouldn't give me U. So you see, this notion of creating a new node is conflicting with the reversibility that is demanded by unitarity. So here are the solutions to these. Here are possible solutions to these problems, and they go by having names of nodes that are a bit more structured, a bit more complex than before. So what I'm going to do is that I'm going to encode edges in the nodes. So for instance, this node is called Y, this node is called Z. There's no relationship between those two names. I consider that this is a graph that is not where there is no edge. Now, if this node is called Y V minus Z, this is the union, the logical OR, okay, whatever. It just agglomerates two names. It's a constructor that agglomerates two names. It's a binary operator that agglomerates two names. Okay, the fact that there is a minus Z here and a Z there tells me that there is an edge. If I take this convention, if I code the geometry within the names, then I'm past this difficulty. For instance, I take the tensor of this guy and this guy, well, it gives me this graph. I take the tensor of this guy and this guy, well, I detect that there is an edge, I can put the edge. Okay? So I'm past difficulty 1 here. Now, let's look at difficulty 2. Yeah?
What seems strange on the last line is that before you're doing the connection, the white circle already knows that it's going to be connected with that. Like you're breaking some form of yeah. Here you already have Z, which is here in white circle.
Yes. I can answer that, but maybe I need the next slide before I do that. Yeah. I can answer all of that in the next slide, I think. Yeah. Okay. So first of all, let me answer the second difficulty, and then I go back to this question. Okay. So the second difficulty is I've got a node U. I've got a unitary evolution that's going to create a new name. How should I choose this new name? I want my stuff to respect, maybe to respect causality, or to, and I want this to be unitary. And okay, so how would I do it? Well, perhaps an intuitive way would be to say, well, I'm going to split the name. This U is going to become a U.L and a U.R. Why not? Whatever this is. I mean, some kind of little operation on names. Some kind of, I'm appending a 0 and I'm appending a 1. So this guy was called 101, and this is 101 O, and this is 101 1. Okay? That's what you do in by the way, in IP domains. You have an IP domain, you want to create 2 subdomains. Well, you just put more numbers and you create your subdomains. Okay. Well, okay. Now, what would U-dagger do? Well, U-dagger, it does the reverse thing as U. Okay, so it's got 2 guys. It should merge them. So what kind of name should I give to that merger? Well, I don't know, maybe V merge with W, with that same symbol that we had before, this V. Okay, let's call it merge. Okay. All right. Okay, so now something weird is happening, because if I do U and then U-dagger, U-dagger is merging U.L and U.R, so it gives me U.L merge with U.R. But this thing ought to be U, because U-dagger ought to be the identity. And so I derive that I need some kind of algebraic property on my names. My names, you know, like 1 plus 3 is equal to 4, right? There is algebraic properties on natural numbers. Well, let's have algebraic properties on names. And here is one algebraic property. The left of U merged with the right of U is U. Okay? Here, if I do U-dagger, I'm going to merge V with W. And if I now do U, I'm going to split this into its left part and its right part. But this ought to be the same as V and ought to be the same as W. Therefore, I should have these equalities here. That is V merged with W, and I take the left part is V. Okay. So what I'm saying here is that at the cost of having a little algebraic structure on names, one can have the best of several worlds. I mean, the fact that I don't want to use the word many. Now, I'm just saying that you can get to have unitarity, this kind of local ways of naming stuff, and this is also, at the end of the day, it's the same algebraic structure that helps you code the geometry. And the point is that, okay, maybe it wasn't so natural to begin with, but then once you've got that, it's nice because every single theorem and lemma that I mentioned before about locality, causality, trace preserving, completely positive map for traceouts, whatever I mentioned before holds in this world. Yes?
Why don't you have the same problem with color?
With color?
Yes. When you generate a new state, how do you choose the color?
No, you don't have the same problem with color because you just need to flip patterns in a unitary way. I mean, so you have to imagine a single node world that has 2 states, right? Now let's look at a 2 node world it has 4 states. So there are 6 possible patterns here if I add the patterns with 1 node and the patterns with 2 nodes. Just take any permutation of those 6 that lets you go from a single node to several nodes. Any permutation is fine. I mean, that's not what's breaking reversibility. Yeah, I'm saying something like I could say white goes to white black goes to I don't know, goes to I don't know. For instance, I could just oscillate these two and be the identity on the rest of the patterns. It's yeah.
Does this depend on having just 2 others, or
No, I think it depends on the fact that that you have finiteness of the number of colors, and yeah, I guess so. Okay. So now let me go back to this question that you had, Pierre. So here you're saying that there is a kind of bias because this node kind of knows that it should be related to this guy, etc. So actually, the fact that there is this algebraic structure upon nodes makes this not very relevant. In a way, what's happening here is that these 2 nodes, they intersect according to this, these 2 names intersect according to this naming algebra, and that's what matters, that they intersect. Okay, this is something I haven't talked at all in these slides, but you can ask for your dynamics to be renaming invariant, to commute with renaming, as we discussed in the paper with Marius and Amelia on quantum superpositions of graphs. And because you will rename this and that at the same time, you will keep the fact, you will give them completely different names, but they will still intersect. And so you will still keep your edge there. But suddenly, it will be, in some renamings, things will appear not so obvious that this guy knows about this guy, but not this guy. I mean, so the point is, okay, maybe what I can say is this. If I have got some node U and node V, I say that they are connected if and only if there exists some word in, I'm taking the left and right, etc., such that u dot w is equal to u to v dot w prime. So if somewhere within the algebraic structure of the names they coincide, then they are connected. And so that's, yeah.
Question which is a bit more general. I see that you're making some formal construction graphs, but maybe what I'm missing is what are the principles that you want to follow to drive the construction? What do you want to do?
Yeah. So I agree that this construction here, this name algebra here, can at the beginning seem a bit ad hoc. Okay, why this symbol? Was it this dot L, this dot R, etc. But yes, they do come from principles, and I thank you for your question, because here really all I'm asking for is that my graphs be dynamical enough so that they may grow, and that I be able to preserve unitarity. And it's just these two requirements that will drive me to these solutions.
We have a somewhat with the tensor.
Yeah, in fact, I can just add that, moreover, I've got theorems that say that in a world of nameless graphs, you wouldn't be able to grow your graph if you want to be unitary and causal. Unitary causal operators over nameless graphs, they can't grow. And if you don't have this algebraic structure, you can't grow either. So it's just...
Why do you make this distinction between colors on the graph, on the nodes of your graph, and names? Because why don't you just have nodes with names and you introduce the color in naming? What's the philosophy about this?
Can I comment on this? Because we had this discussion 3 years ago.
Okay.
Both studied the discrete process connection. So there's something missing when you just label a graph with spins, which means that you are doing at the same time coloring and naming. So you're not distinguishing between colors and names. Yes, which is that basically what you do here with the naming is putting topological construction. What is putting the topological construction? It's just constructing the graph per se, explaining what are the connectivities, giving the adjacency matrix that defines the graph. And all the stuff that has definition of unitarity, of locality, of causality, they can be defined at that level. When you do like spins on a graph, you are at the same giving colors and names. Alright? And this for me, this is basically a mistake. And this is why they cannot see the relevance of this remaining variance. Because it is just related in variance to get the threshold in that case. So for him, I think, I don't know if he completely agrees, but the point is with the names, you just sort out what's going on with the connectivity. And then on that structure, you can put whatever theory you want in terms of physical fields. It's like having a manifold, and you have the manifold. The manifold has some topological structure, some directional structure. That's before you put anything on it. Right?
Yeah, so the colors are fields, whereas the names, they are like a kind of system, coordinate system that you lay out on your graph, just to be able to talk about this node or that node or that node. And in particular, when I want renaming invariants, I want renaming invariants under renaming those things, but not under changing the fields. The fields, they're not affected by renaming. Okay. You wanted to say something?
Yeah, I mean, I was also, he's very facilitated. So many things, the impression is like that, but I think this is still fine what you're doing. Like, you put these cats everywhere. And actually, even if you don't do these cats, put cats everywhere, it will work. This is just because it seems like, at least on the figures that you show us, is like having always in one basis quantum mechanics. Like, you never talk about that. It's still not clear what, how would you prove that this is just not a classical mixture of all states that you could make. You put the cats, so that means, okay, this is not a classical mixture, although the graph looks like classical mixture. But you put a cat, meaning it is more than that. But this, I feel this you can do this, because then you have a unitary indifference. It's like measuring everything in position basis, but having unitary in between, that will tell you something about all other bases. But it's known result like in quantum mechanics that if you just look at the state in one basis, you are indistinguishable from the classical mixture. It's just like you have a superposition 50-50. And you should measure it will be 50-50. So the only reason why I write cats is because I can do something like an interference experiment. Now this interference experiment in your approach can be encoded hidden in the unitaries that make like one graph into the superposition graph.
Yes.
And somebody would ask you, how do you know it's a superposition graph? Because I can make an inverse unitary and bring you back. If it were the classical mixture I want. So I guess you do have this formalism, and I somehow feel like that's where you have to put focus as well.
Where I have to?
Put the focus in justifying that these are really cats.
Yes. So, I mean, the way I would rephrase this comment is rather that I'm in a picture of quantum theory here, where you have states, they evolve unitarily, and that's all what's happening. And I didn't pronounce the word measurement almost. Okay, I spoke about this in the Heisenberg pictures and stuff, but it's a kind of fully unitary evolution way of looking at things, and yet you can model measurements very well by means of traceouts, right? I mean, that's what I was talking about. Yeah, I mean, as soon as you have a tensor that lets you split stuff and then a traceout, you can actually model measurements. So I haven't been talking much about what is observable, how this evolves, etc. And I mean, this picture, things evolve unitarily. What if you want to measure? Well, I don't know. I'm not telling you if you want to measure.
That much about the measure. I think like this theory could be a theory of classical graphs. In spite of the fact that you put the cat, because you didn't explain what is the cat. So I say, no, this is just a classical mixture. And then you say, now I make a superposition. I say, no, this is just a classical mixture still. Then you apply unitary. I say, no, this is just a stochastic matrix. So how should I ever know that it is a quantum? And I think you can, because the unitaries should be such a very strange one.
Yes, I mean you can just put you can model any quantum walk, any quantum cellular automata in there. I mean, you can just put a hell of a lot of physics in that formalism. So I mean, I'm not at all worried by that. But so I guess maybe you mean something a bit different. Maybe what perhaps answers a bit this question is examples. So so here is so here is some interesting local operation you could do. You could have a local operation that looks at entirely black nodes and decides to split them into two. So this is dynamical. Sorry. Actually, it's the reverse way around here. I'm looking at this pattern, and I'm splitting these two into three, or the reverse way around. I'm looking at this pattern, and I'm bringing three into two nodes here. So this is something that is dynamical on the graph, and you can actually choose to make this quantum, and with some amplitude you will do nothing, and with some other amplitude you will actually perform this kind of a merger, and you need to make sure that your amplitudes are unitary, so there is a little unitary behind. So so if there is no dynamical geometry, I would say answering your question is kind of easy because I can model whatever you want in quantum CA, whether the Young slit experiment or anything. Now that geometry comes into play and begins to be superposed, I should think that there will be interference effects there as well. And I could make some toyish trivial example where this is the case. For instance, maybe iterating this guy should give you the identity for well-chosen phi. Okay, but it's a whole field that remains to be explored.
This half, black half, right? This is kind of like if I put a spin on them, this is a superposition of spins. What does it mean, half, white, half, black?
So here there are two particles. Here there is two particles at that node. One is spin left and one is spin right. So they kind of collided there. And when I detect such a pattern, I decide that, okay, maybe I need a bit more space to put these particles, so I'm going to inflate the graph a bit. And then with some amplitude, I actually separate these two particles in positions like that.
Is this a superposition of the field on the graph? Or the superposition?
So the superposition is here. This is superposed with this. And here there is a superposition of both the shape of the graph, this graph has got 5, this graph has got 4, and of where the fields are. Okay, so you can start looking at local evolutions upon graphs where you create superpositions there, right? So maybe I should have found, where was this picture? Yeah, so in general, a local operator over a graph is going to be something that looks at a node, looks at the neighbor, and it's going to replace this disk by some disk or another in a superposition, but all of the rest of the graph is going to be left unchanged. Those are these local operators over graphs. That's how they work, really. Yeah?
Just to comment on what I was saying before, that this is something one thing that was missing from group quantum gravity when I was learning. What you do with the labeling when you have graph change. Usually we take 6 graphs. This is one of the main things. With these things.
Yeah, if you take unitarity seriously and you want to change the number of nodes, you run into serious difficulties. Yeah, that's the point. Yeah. Okay, so maybe an example of a causal dynamics would be to have particles that move and they are quantum walkers, so I act on a coin, and then sometimes they collide, and I apply this thing. So that would be some kind of a little toyish model of something that is quantum, that is dynamical in terms of graphs. And actually, we've had an intern, Joseph Touzet, to try and simulate this, because when we do it in Python, we can get to 5 iterations, and he's been doing this on supercomputers, and he got to 10 iterations. Okay. All right. So let me just summarize what I said. So I started with the idea that perhaps the tensor product needed a more precise notation of whom goes left and whom goes right, and realized that actually we could parameterize the tensor product by any restriction. And those splitting, therefore, of the Hilbert space gives you a valid tensor, and entanglement is relative to that parametrization. Okay. So why do these generalized tensors and traces work? Well, they work because they mathematically, they serve just the right purpose that you want tensors and traces for, that is to speak rigorously of locality and causality. In different pictures, whether the Schrodinger, operational, Heisenberg pictures. All of the logical interrelations between the concepts are safeguarded. What are the applications? Well, for instance, you can use this to take the point of view of a superposed observer, but